Hello, everyone. Today I'm going to talk about a cognitive approach to meta science and technology. I'll begin with a bit of background. My PhD was from the University of California at Santa Cruz in the Department of Psychology, but my dissertation was doing computer modeling of how people put information together between vision and hearing in virtual environments. That was a bit of an unusual dissertation for psychology. So after a postdoc or two, I ended up at UBC's Media and Graphics Interdisciplinary Center called MAGIC, with faculty appointments in commerce, computer science, and psychology. Magic was very interesting to me because it crossed disciplines and units to build interactive media technology for organizations and individuals. We were kind of an interface between the broader capabilities of the university and different industry partners. We were housed in the Faculty of Graduate Studies. We had an endowment. And so we could take along there in grad studies and not offend any deans because graduate studies is the university's answer to Switzerland. It's mostly neutral. At a certain point, SFU, nearby Simon Fraser University, came up with the idea that they would create a school of interactive arts and technology that focused on interdisciplinary tech design. I took a leave from my salary at UBC, but kept the appointment and moved to Simon Fraser University to help start that program up. In the broader academic community, my career has mostly been in IEEE, in the Visualization and Graphics Technical Committee, place where all of the richly interactive interface work in IEEE happens. I've been involved in the Visualization Psychology Group. I'm on the Eurostar's independent expert panel that funds cross-EU collaboration in industry and with universities, NSERC, our answer to NSF, and the High Bar Research Alliance. Most of my work in the lab is collaboration with tech companies and organizations in different areas. Some examples of some lab work: we've done a lot of work on aircraft design and safety for safety analysis, funded by the Boeing Company and MITACS, a Canadian granting organization. We've done work in emergency management, building a virtual emergency operations center. A lot of work in healthcare, multi-omic personalized health, public health, medical images for cancer diagnoses. And then very recently, we've started to work in food and the environment with some decision intelligence approaches done in collaboration with Quantalia. I'm going to start by talking about visual analytics. Visual analytics is a new field of study that combines science and technology to understand how we reason with interactive visual interfaces. Visual analytics is a little over 15 years old. It started with an R&D agenda panel at Battelle's Pacific Northwest National Labs. After 9/11, the US realized that they needed to find different ways of dealing with intelligence analysis, criminal analysis, and so on. And so they brought together a bunch of people at USPNL in Richland, Washington. There were a number of universities, industry, and government agencies there. At the end, they created the National Visualization and Analytics Center at PNNL, an industry consortium, and DHS chartered a second organization, Visual Analytics for Command, Control, and Interoperability, that brought all these universities together to understand basically visual analytics. Well, visual analytics is an interesting field. It's a multidisciplinary field. I could define it for you, but I'm going to let Jim Thomas do that. This is an old video from Jim Thomas at PNNL, who really led this effort.
A history of where we all started, and a lot of us in this community started in scientific visualization, where we're working mostly with these nice science numbers. Had a good science foundation. Then we went into information visualization, where we were dealing with abstract information spaces. The reason that neither of these are addressing these is now we need to get into the decision sciences, the analytical sciences. How do we actually make decisions when we're posed with all of this information? And that requires different disciplines that are traditionally involved in these two core sciences. It involves decision sciences, cognitive and perceptual scientists on a whole different degree, but it also involves the database folks and the knowledge engineering folks. How do you represent information? How do you build knowledge structures that can then be used in order to make decisions based upon these structures? So it's a much broader science agenda. And so you'll see a lot more interdisciplinary teaming, actually interdisciplinary. This is going to be a contact sport, if you will, in terms of being able to do this. And so we don't want to do this separate from these other communities. What we want to do is engage these other communities.
So if you look at the Grand Challenge document called Illuminating the Path, IEEE Press, it's online available as a PDF, you'll find things like this. The science must be built on integrated perceptual and cognitive theories, on the dynamic interaction between cognition, perception, and action. It must build knowledge about psychological foundations of concepts such as meaning, flow, confidence, and abstraction. So this is a heavily cognitive effort. It's not really just computer scientists building graphical user interfaces. It's really a cyber psychology. Well, that was the US effort, but a similar effort started in Europe and ended up with some coordination action that followed on a German DFG Scalable Visual Analytics Priority Program. So these were big efforts. They redefined visual analytics or extended the definition a bit. Visual analytics combines automated analysis, and we're talking about artificial intelligence as well as data visualization, but they're still focused on understanding, reasoning, and decision making. And a bunch of us got together with our EU colleagues and we wrote a paper, From Visualization to Visually Enabled Reasoning, consistent with the original definition of visual analytics, but now it's extending to reasoning in a more general sense. So if we look at visual analytics as a new cognitive science, what do we draw from the old cognitive science and what areas of research are important to it? One area is what we call the cognitive architecture of human vision. The basic elements, the Lego blocks, if you will, that the visual system puts together to solve a cognitive task, the capabilities that vision gives us. Think of things like visual perception and attention. What can we see in this complex graphical interface environment? Much of this comes from the neuroscience, but a lot of it's done in experiments conducted in laboratories with reduced Q environments. Now we have to extend this to rich sensory environments. So we're working with a much richer palette of experimental designs than you can typically see in vision research. We also have to support higher level expertise, the perspectives and expertise that happens when people work with these images for a long period of time. Think of a radiologist looking at different medical images. They're going to see those in different ways. They're going to use spatial attention in different ways than you or I will. So we have to adapt and personalize these visual analytics environments to support that expertise and to recover different perspectives of different stakeholders. Of course, these people work together. So the last hurdle we have to leap is understanding how people use these environments for collaborative decision making and how to design these environments for better collaborative decision making. Some of this is captured by the decision intelligence approach that's getting a lot of attention these days. The book that Lorian Pratt wrote, Link, is really one of the core documents of this field. Decision intelligence is a new approach to AI augmented decision making in organizations. Well, of course, my day job is in the university. What does a university bring to the table? Well, we want to be an agile and responsive university. One of the ideas that we got from some documents, this is about 20 years old, the new production of knowledge, is to think of the university as having two modes. One mode is producing knowledge, which we do through standard research, scientific research, and training students in that knowledge, and they go out and get jobs and live their lives. But there's another capability the university has that's really familiar to many of us. Companies and organizations come to the university with a problem, and they want us to put our different parts together, bridge our different silos, and help them with that problem. The goal in many of these is the wise design of socio-technical systems. This was true of a lot of magic projects. We were building technologies, but we were also building technologies for a particular organization, for a particular collaborative approach. And the design is to be wise in that it supports that approach. It's not just technically good. It's something that takes into account the values of the organization. Of course, in order to do this work, you have to engage your community partners. You base it often on regional advantages. In Vancouver, we have the national supercluster in digital technologies. We have a big agri-tech group. And so those are areas that we try to support. We, we value the incubation of new ventures, attracting capital. And so there's a bit of a business school side to this as well. But since we're a public university, we have to always consider the value to society, ethics, governance, sustainability, and so on. Of course, since we're also a university, we have to feed that back into our instructional programs. We want our students to be able to say that their knowledge in different content areas, these are not all business students, these may be students in psychology, that psychological knowledge is a competitive advantage. You should hire our students because they know how to use psychology for the benefit of your organization. And we should feed that back into our instructional programs. We know how to do some of this, and this is some very recent writing, especially the Techno-Scientific Revolutions book. It's from the Dean of Engineering at Harvard and someone from a US National Lab. There's a work of science where they find facts and explanations. There's the work of engineering where they find functions and they build forms. And then in the middle is this very interesting space where you control the movement of information between science and engineering in such a way that they can both stick to their knitting, stay in their lane, do their job, but it's an informed way. That T shape in the middle is a very interesting organizational psychology, organizational cognition approach. How do you build an organization that integrates in a highly integrated way? That's the high bar approach, science and engineering. And so there's a bit in this book, and there's an awful lot of know-how that you get from working in these organizations that helps us to build, as they say, techno-scientific revolutions. So that's a very brief description of the future of visual analytics as it exists now. I'm going to talk a bit about the future of visual analytics. So where can visual analytics go from here? Currently, we're pretty good at bridging science and engineering in order to design these systems. We can scale to advanced information systems. It's a cutting edge research area, but we look at how to build for more complex data spaces and for more complex situations and how they can be represented in those data spaces. We are looking into human AI interaction. The computer can no longer just be a tool that performs a task. These AI agents have, in fact, agency. They are taking actions that the user did not tell them to do. They're coming up with new ideas that the user has to understand. Again, we don't want that system to make the decision for the user, and we don't want it to be just approving a situation. We want rich interaction between the user and the AI, as human AI teaming, human-centered AI are some terms that we use. At some point, the rubber has to meet the road. So we have to be able to demonstrate a positive impact on decision making. At the same time, we're building these systems for 10 years in the future. We have to be able to incrementally improve the decision making in organizations today. We have to use what we know now to give our industry partners and government partners and not for profit partners an advantage in how they make their decision. So we've done a bit of that, and it's something that is ongoing. It's a hot area in visual analytics. Where I think visual analytics falls short is a lack of engagement in the creative design community. The missing piece is design. How do we build environments that represent problems that are very complex and don't have any intuitive traction? For example, we did some work with Banff Center for the Arts that looked at building um, collaborative R&D systems for software support systems for nanotechnology researchers. Well, the phenomena they deal with aren't really mappable onto our everyday life. So however we represent these phenomena is going to be creative. It's going to be, in a sense, artistic, but in a kind of functional art. So here's a quote from a book I'm about to introduce, The Nexus. Design bridges, I'll say ought to bridge, the domains of art, technology, and science. So this is a book that was published just a couple of months ago by Julio Mario Otino and Bruce Mao, the famous designer. In the design community now, we understand something about a design rationale, which is a science-based engineering desiderata that the designer should use, should take into account when they do their creative design for some interface. We integrate cognitive psychology in those design rationales. Nexus thinking asks us to move a step further. Can we extend meta science and technology, if you will, to include the creative art in a much more fundamental sense? So, can we engage artists, engineers, and scientists in a three-way interaction, something that goes beyond technoscience, that will give us the kinds of innovative solutions we'll need? Now, as a cognitive scientist, I have to turn back and say, what does a cognitive science perspective on the design process look like? Can we understand the cognitive science of nexus design? Well, this is a very interesting area, and it's an area that is, it's really, unknown territory at this point. But it does reflect back to some of the goals of some of our early computing researchers. In many of my talks, I give a shout out to Doug Engelbart. He's best known as the inventor of the mouse, but he's better thought of as the inventor of many of the technologies, the software technologies that we use: computer-supported collaborative work, joint editing of documents, teleconferencing. His goal was to build a collaborative community of knowledge workers that would bootstrap their way up into more advanced augmented cognition approaches. And I was honored to work with Doug in a group called the Engelbart Dialogues, to host him in Vancouver for a talk here. And this is a slide from those days. Thank you very much for your attention, and I look forward to chatting with you in the discussion.